For centuries, fashion has been limited by the physical properties of thread and fabric. A designer might imagine a gravity-defying drape, but those ideas are often impossible to execute due to the strict requirements of material tension and weight. Traditional drafting builds in a technical ceiling. Pattern making relies on translating three-dimensional curves onto flat planes and right angles. If a shape cannot be constructed from a two-dimensional sheet on a cutting table, it remains a sketch. Generative AI acts as a silicon loom, processing design through computation instead of physical threading. This shifts the medium of fashion from tangible material to pure data. This diagram illustrates that transition. The algorithm takes a standard pattern and converts it into a multi-layered simulation matrix. It calculates thousands of fabric behaviors, sheen, drape, and elasticity at 8K resolution before a single stitch is ever cast. Moving from matter to data allows designers to prototype silhouettes that were previously unbuildable. They can now verify the structural integrity of mathematically complex forms within a digital space. The digital canvas removes Euclidean geometry as a flat grid warps into a 3D manifold. Through algorithmic tessellation, a continuous loop forms a sleeve, mapping mathematical folds around a wireframe limb, creating structural volume independent of physical textiles. These structures are impossible to draft using standard patterns. Standard tailoring relies on darts and seams that physically cannot accommodate these continuous multidimensional loops. Designers now engineer complex spatial anomalies, expanding the vocabulary of garment construction far beyond the historical limits of the cutting table. With spatial constraints removed, the simulation next addresses the mechanics of gravity and material weight. AI calculates stress distributions, predicting how a garment balances by analyzing localized pressure in a virtual environment. As extreme cantilevers extend, heat maps dynamically redistribute, showing how the structure maintains a perfect mathematical balance that would be unstable in reality. Every pixel in an 8K canvas functions as an individual thread. Each one reacts to simulated tension and light refraction with granular precision. At 8K resolution, digital renderings trigger physical instincts. The simulation is so precise, you can sense the weight and friction of raw silk. Algorithmic optimization stabilizes these forms, allowing precise control over balance independently of physical intuition. The simulation modifies the foundational canvas, the human body. This digital mannequin morphs to elongate its limbs, stretching far beyond natural anatomical proportions. Digital algorithms ignore skeletal limits. They break biological symmetry, treating the human wearer as a set of coordinates, not a fixed anatomical structure. This enables a post-human silhouette. Designers can craft garments for asymmetrical torsos or weightless environments, where the body's natural shape is only a minor consideration. To ensure these garments function, the AI processes thousands of micro-adjustments per second, testing volume and proportion against radical new body types. In the digital frontier, the physical human body serves as a flexible parameter, a suggestion for the algorithm rather than a fixed boundary. As digital environments become the primary canvas, traditional tailoring logic loses its practical necessity. When a garment is built for rendering engines and augmented space, physical seam allowances and construction marks are no longer required. Fit is now determined by visual impact and the garment's reaction to virtual physics, rather than matching a standard size chart. The workflow has evolved into a cyclical digital loop. Intent feeds the algorithm, which passes through physics simulations to produce a final output. This turns the designer into a digital architect of complex visual ecosystems. Mathematical imagination now dictates the limits of fashion, reaching as far as a rendering engine can calculate. The result is a shift from physical construction to the management of simulated physics.